This talk is actually a lot longer than the time that we have because there's a lot of information to know about PMDK. And so I've tried to boil the slides down to the stuff I think you're most interested in. But there's a massive amount of information available. All of these slides will be made available and posted on the web, so you don't really have to spend a lot of time copying anything down. And the slides are full of references to other locations on the web for more information. Right? So we have an unbelievable amount of information about programming. So here's what I'm going to cover. I thought I would just start out with the essential persistent memory concepts, what everybody needs to know about persistent memory. A few things about the OS support, the essentials about the PMDK libraries, and then I go into some of the essential details for the libraries themselves. So let's dive right in. So persistent memory. You know, when I started this, we could have just said that persistent memory is access like storage and that's it, right? And what does that really mean? So this is my cartoon of what storage looks like. And this is what storage has looked like for many decades, at least my entire career, which is, you know, older than a lot of people in this room. So, you know, basically the storage stack tends to have some amount of storage that is directly attached to the system, and the system has some set of drivers. I just kind of, without too many details, I just say driver. And then applications are free to access block storage directly, right? This line here really stands for a very simple API. It only has two operations, read a block and write a block. That's what block storage can do. It can't do anything else. So that's why we put a file system on it, to make it more usable. So a file system converts blocks into files, right? So this is the standard file API. So on Windows, this is the Win32 API that's been around a long time. On Linux, this is POSIX, right? So there's some standard file API in storage. So it all pretty much looks like this. And what's interesting about this, if you're a programmer, is that storage APIs are buffer-based. You really have no choice but to pass buffers around. So this is some C code. If you're a programmer, you might recognize this. This is how you open a file on Unix systems, right? It's very simple. You get back this little file descriptor, and you can do reads and writes to the file by using these system calls called read and write. Now, it may be that you look at this and you say, you know, I've never called these. But if you've ever done I/O to a file, you have called these. It just might be through a library, right? So like in C++ or in Java, if you use something that gets data from a file, these are the only choices, right? The libraries have to call these. These are the entries into the kernel. This is how the kernel offers to do I/O. And notice the second argument here. It's a buffer. In other words, I can't read from storage unless I supply a DRAM buffer. I'm making a big deal out of this because this is different from persistent memory. Right? Persistent memory, you can access your persistence in place. That's what's so cool about it, right? And storage, the API doesn't allow that, right? It's a buffer-based API. Well, what about mmap? What about the memory mapping of files? Well, so in storage, again, for about 30 years, we've had this thing called mmap. On Windows, it's called map view and file. And it's been around forever. And what happens is, you map the storage here, and then you get to do byte addressable access. So you can see here, after I get something back from mmap, here I am in my program just accessing it with loads and stores, right? Just pretending it's an array or it's a pointer. Here I'm doing a stir copy to it, right? So this is the load store block, okay? So for persistent memory, I'm talking about this because for persistent memory, these memory map files are going to turn out to be really important. Well, so if mmap has been around for 30 years, how does it work? Storage can't talk in loads and stores. Storage can only talk in blocks. So how does it work? It works by really mapping to the page cache. So inside the system, there's this cache of pages. And when you call mmap, you really map to the DRAM page cache. Okay? And what happens is, every time you access something that doesn't happen to be resident in DRAM, it gets page jammed with page fault. And every time you want to flush your changes to persistence, those pages get pushed out. They get evicted from the page. So this is actually not that common. You know, a lot of people, they get through a computer science degree in school and they've never heard of MNAP or they've never used it. But it's actually used a lot more than you think. Let's see, I see some laptops open in here. Those things are doing MNAP right now because it's actually used a lot in the runtime environment for things like macOS. Right? It's used because that's how they get to things like shared libraries. They use memory map. So it's actually pretty commonly used. It's just mostly system programmers know about it, and application programmers don't think about it. It might be a little more common than it seems. And so, like I say, you're really just mapping the page cache. And here's the thing that some application writers don't like about MNAP. If you access something that doesn't happen to be resident in DRAM, then your program is put to sleep while you do a page fault. Okay? So this is the thing that application writers don't do. Right? This is why big databases like Oracle and SAP and those guys, they don't use paging because they don't like the surprise delay while you're waiting for I/O. Okay? But again, persistent memory, you access things in place. So we can get rid of this with persistent memory. Okay, so you all kind of know about persistent memory. If you saw my talk this morning, you know that there are these things called NVDIMM-Ns that have been around for a long time. But I think you also know from the talks that you've been hearing that Intel has this persistent memory product, and this is what motivated me to get involved with this and start looking at what the programming model should be. This is all a lot of marketing information here. The really important part, as far as we're concerned in this class, is that it connects to the memory bus. Right? So it's not a storage device anymore. Now it can do local storage. So what's motivating about that? Why do I care? Why can't I just use the storage APIs? They've been around forever. Well, here's a little graph that shows you where the latency is when you do I/O from a device. So if I just take a NAND SSD, just off the shelf, one of Intel's NAND SSDs, and I want to read the smallest amount of data I can. I just want to get 1 byte off of that SSD. Where is the latency? Where does it spend its time getting that 1 byte? Well, you can see the green bar here is the software stack. This is like the driver in the kernel, and so on. The blue bar here, that's the actual hardware. That's the flash media time. Right? So it's taking most of the time here. I could go in and I could improve the driver in the kernel. I could make a faster driver, twice as fast. And it really wouldn't change the situation. Because the driver is only a tiny sliver of the latency. It's the media that's taking all the time. On the other hand, what about an Optane SSD? Intel released those a couple years ago. It uses the Optane media inside. Now look at the blue bar. It's much smaller now because Optane media is so much faster. Look at it in comparison to the software stack. They're about half and half. So now it's suddenly motivating to do something about that software stack. Now, if I make an improvement to that software stack, I'm making a bigger percentage improvement to the overall latency. So I'm much more motivated to do something about the software stack. What if I could just, try and remove that stack completely? If I do that, this is what I get. Here's the NAND SSD, here's the Optane SSD, and then with persistent memory, I can just remove the software stack completely and let the application talk directly to the media. So look at the blue bar now, and there is no yellow bar. It's gone. So this is really what's motivating us to have a different programming model for persistent memory. This is why we're not just using the storage APIs. Storage APIs all require the software stack. Our new programming model doesn't. Once you map this stuff, you have direct access. Okay, so let's talk about how this works. So this is the programming model. This is what was motivating by the last slide. At the bottom here, you see persistent memory. This is all the persistent memory in the system. I don't show multiple DIMMs or anything. Let's just think of it as one big pool of persistent memory. when the system boots, the fact that it has persistent memory is communicated to the operating system using a new table that we added to ACPI. So when the system knows that it has persistent memory because of this new table, there's a new driver. The drivers are called different things on Windows and Linux, but this is a generic programming model. So I just call this the .mvdim driver. It actually has different names on the operating system. So this driver takes ownership of all the persistent memory in the system. And it provides these three paths. On the left here is the management path. This is for configuring your persistent memory or checking its current health status, how worn out is it, stuff like that. The middle path is the legacy storage path, right? So remember I showed you that storage cartoon a few slides ago. This is that same thing. Applications can talk directly to the driver. Applications can talk to a file system to the driver. They just think they're talking to a really fast SSD. These are unmodified applications, okay? No modifications, this just works, right? But we can do better than that. Like I said, we can get rid of the software stack. And that's this right-hand side of the picture. In the right-hand side of the picture, we create this new thing, this green box here, called the Persistent Memory Aware File System. With the Persistent Memory Aware File System, when it starts up, it asks the driver, "Are you persistent memory?" And the driver says, "Yes, yes I am." And at that point, this file system knows it can use this blue arrow right here to talk directly to the persistence. Right? It can do loads and stores. So if I, in my application, if I call a read or a write, instead of going through the block stack like it used to, the application just calls into the file system, and the file system can just satisfy that read and write directly. So if I just stop there, we're better off. We have a little bit faster file layout. But I don't stop there. Of course, the whole point here is what happens when you call mmap. When the application calls mmap, you end up on this far right blue arrow. And that's where the application has direct load store access to the media. Okay? So just to make sure everybody knows what I'm talking about, here's the application. It's mapped some persistent memory. If I do one store instance, one load instruction, I am loading from the media right here. There's no kernel code, no operating system involvement, no interrupts, no context switches. Pretty cool. And so you can see if I use the left-hand side of this diagram, if I use this, I'm basically getting persistent memory to look like an SSD. If I use on the right-hand side of this diagram, I use my persistent memory aware file system. Again, it's just like an SSD, only now there's no caching. There's no need for it, because I can now access the device directly with both servers. So, really, it's not until I decide that I want to do something special that I even move to a new interface. So far, we've just been talking about standard interfaces, right? So, what happens if I use standard interfaces and I want to memory map a file and make changes to it? So on Linux, if you memory map a file and then you do some stores, those stores are not persistent until you call msync. It's the same on Windows. If you call map view a file and you do some stores, those stores are not persistent until you call flush view a file. Right? There's a flushing step. It's been there forever. It's been there for 30 years. So even if I do this here, if I call mmap and I do stores, I have to call msync. Well, you know, historically msync is about flushing the page cache. There's no page cache over here. There's no caching. So what is it flushing? It's flushing the CPU caches. That's what needs to be flushed to make something persistent. So when I call msync, msync goes into the kernel and it says, oh, this is persistent memory. All I have to do is use this instruction to flush the CPU caches. But that instruction is not a privileged instruction. It can be done from user space. So we can make this even faster. We can move outside of the POSIX interfaces and add one more call here, which we call optimized flush. Optimized flush is where you flush changes directly from user space without any kernel involvement. Right? So now we really are direct access. We are as fast as you can make it. So this is the basic programming model. This is how operating systems expose persistent memory. After that, what do we do? Well, you know, like I said in the talk this morning, we are used to, as C programmers, we're used to just calling malloc to dynamically allocate memory. So why don't I just say persistent memory malloc? And the answer is, well, then what? You allocated the memory, but How do you make sure that you had permission to allocate it? How do you reattach to it by name the second time you run? How do you make sure that it doesn't leak? So there's more to it than just that. The other thing that's kind of interesting is if you look at these traditional interfaces, this comes up a lot. People say, wow, persistent memory is hard to use because my changes are visible to other running threads before they're persistent. Is that a bug? And I say, well, no, that's just how POSIX has always worked, right? In POSIX, if you memory map a file and you do a bunch of stores, everybody can see those changes. But they're not persistent until somebody calls them. So it's just something you have to be aware of. In the hardware, how does this work? Well, in the hardware, here's a little cartoon of an Intel processor with some caches. In the hardware, if I do a store instruction, it goes down into the processor caches. It eventually makes its way through the caches to the memory controller, which I showed down here. And then eventually it makes its way to persistent memory. So, what I really want is the moment I do a store, it's persistent. But that's really not practical in today's hardware because these caches are really huge. And to make the stores immediately persistent, I would either have to make these caches right through, in which case they wouldn't be fast enough. Or I have to make these caches flush automatically if you lose power, in which case the system would have to have a big battery. Neither of those are very practical right now. So instead, what we do is we say, a store is not persistent until it's accepted by the memory subsystem. So when you get into this red dashed box at the bottom, that's when something is considered persistent. It doesn't have to be all the way to the end, but it has to be inside the red box. Okay, so that's how the hardware works. How the software works is a little more interesting. Every app that uses persistent memory has these responsibilities. When it starts up, it has to decide, do I have direct access? It has to decide, are the CPU caches persistent on this machine because somebody wired a big battery to it? Or are the CPU caches something that require explicit flushes to make something persistent? If you do require flushes, is the CLWB instruction available? If so, we should use it. If not, we should fall back to using this instruction called CLFlushOut. If that's not available, we should fall back to this instruction. So you can see there's a little algorithm that every program should do at the beginning. And this is kind of boring programming, right? This is not exciting. In fact, it's so boring and it's so, boilerplate. It's the same at the top of every program that you really just want a library to do this work. But of course, PMDK will do it. Similarly, we have, as every app starts, it has responsibilities to look to see if there are any data loss scenarios. This is a situation where you might have gotten an uncorrectable error and you've lost data in your persistence. Now, we have a way for checking that, and you want to be able to recover from it. And again, it's a little flow chart. And again, it's kind of mundane programming that you don't want to do for every program. You want to use a library. So that's really the reason why we have PMDK. The point of having PMDK is to take that very simple path I told you about before, that direct access path, and just add in the stuff that you need that's kind of mundane boilerplate. Add in the stuff that checks for how do you flush persistence? How do you check for bad logs, that kind of thing. That's all in here. On top of that, we add some stuff to the runtime to give you support in different languages, Java, C++, so on. And on top of that, we add some tools for correctness to check for programming errors. So the result is what we're here to talk about. So let's just touch on this. We have done a lot of enabling in the ecosystem. The picture that I showed you, the programming model picture, it went into Windows, it went into Linux. Here's the versions that we recommend that have all of those things implemented. You can see there's a certain Linux kernel version. When I mentioned a persistent memory-aware file system, on Linux it's these two file systems, ext4 and XFS. Okay? On Windows, the persistent memory-aware file system is NTFS. Okay? And they use these file systems with persistent memory by putting the file system in a mode called DAX, D-A-X. Stands for direct access. Right? So on Windows, it's an option to the format. When you format a file system, you say format, drive letter : /DAX. On these file systems, it's a mount time option. You say mount -o DAX. Right? But the feature is the same. It's called DAX. That's what you look for in your operating system to see if you support persistent memory. I also point out here we have support in VMware. Some of the distros are already supporting most of them by now. We add support to the Java JDK for persistent memory, and so on. There's more information about these, and in particular, each operating system has its own commands that you go through for provisioning and configuring. We had a great webinar on how to do the provisioning of this stuff done by Steve Scargill. I put the link in this slide here, so you'll be able to find the slide when we publish it and follow that link. Okay, one more concern that I wanted to make everybody aware of is that, remember, I said we were using all standard interfaces until we got to the point of doing that flush from user space, which I call optimized flush. On Windows, if you have DAX, then it's safe to do a flush from user space. In other words, if you memory map a file and you do stores to it, you can use user space instructions to make those stores persistent. It's safe. On Linux, it's not safe unless you get agreement from the operating system. And that's a new flag down here to mmap called map_sync. It's not something you typically have to worry about unless you're writing your own library. PMDK knows how to do all this. I just want to make sure you're aware of it. If you decide not to use PMDK, of course you're free not to use PMDK. You can access the persistence directly, but you have to follow the rules, and this is one of the rules. Okay, let's talk about the libraries. Let's get into it. So, we wrote a bunch of libraries. We call them the Persistent Memory Developer Kit. It's really a big collection of libraries. It's about 10 or 11 libraries right now. The libraries that matter the most are what I'm going to talk about right now, because this is the essentials area. But you can see there's actually quite a number of them. And the most important thing that you get from this slide is there is a sort of a layering to them. There are these low-level libraries down at the bottom called libpmem and librpmem. Libpmem is for local persistent memory. Librpmem is for remote persistent memory. That's persistent memory that you access over RDMA. And then we have libraries that build on top of that. pmemlog, pmemopt, pmemblock. Those libraries provide higher semantics, higher level semantics, and they build on these smaller libraries. And then on top, you can see we do different language runtimes, different bindings for different programming languages, and so on. We've built some other things that are kind of shown off to the side here, and there are talks about these things in the summit. There's a talk about PMMKV coming up today, and I think it's actually tomorrow when there's the talk about the C++ interfaces. And I highly recommend those talks because that's where you really see the nice high-level APIs that we provide. Off to the side here is also the volatile support of persistent memory. So persistent memory is persistent, right? That's why we call it that. But that doesn't mean that you always care about persistence. It's big. It's big and it's cheaper than DRAM. So a lot of the use cases we've had are not caring that it's persistent. They just want another tier of volatile memory. And so we've made a couple of libraries for that use case, and that's the ones that are over here in green. Okay? So how do you decide which library is the right one for you? Well, there's a kind of a decision process you go through. The way to think about it is this. We have ways of using persistent memory that are very easy. They're very simple. There's no barrier to adoption. There's almost no change that you have to make. They're very easy. On the other hand, we have ways where it's harder and harder to adopt persistent memory. The farther I go to the right, the more work. Right, this is like modifying my code, modifying more code, designing more changes to my code. But look at the gain, right? The harder I work, the more I do to my program, the more payoff there is. So it's a trade-off, and you have to decide where your use case fits on this continuum here. Now, let's just go through the continuum with a few examples. Over here, the Optane DC persistent memory product that Intel ships has a thing called memory mode. Memory mode is completely transparent. In fact, it's so transparent, even the OS doesn't require modifications. You just put it in memory mode, and the system looks like it has big memory. It's volatile, it doesn't use the persistence, but it automatically makes the system look like it has huge memory. So this is pretty easy. On the other hand, you get the least benefit here. Yeah, you get bigger memory, but there's a lot more value you could get from persistent memory by moving to the right. The next easiest thing to do is to kind of move over to the right and use the persistent memory, again, without caring about the persistence. You use it in volatile mode. But you modify your application. So if you modify your application, you use libmemkind. That's an allocation library that knows about different kinds of memory. You could say, oh, I want to allocate DRAM for this data structure, but I want to allocate persistent memory for this data structure. And what you can do is, in your program, you can put the really hot data structures, the data structures that require the best performance, you can put those in DRAM. And then the ones that are not so hot, but maybe they're large, you need the capacity, you can put those in persistent memory. We've had a huge amount of benefit in applications modified this way, right? Because first of all, it's pretty easy. There's a very low barrier to adoption, and you start to see some pretty good value. So on our website, on our GitHub area, there's a version of Redis that does this, and we've actually had a lot of success there. There are some commercial databases that are already doing this. So this is something that's pretty easy to do, and it requires what I would call a fairly straightforward modification to your application. If you're not willing to modify your application, yeah, maybe memory mode's good enough. But this will always beat memory mode. You always get more value. Because your application can always make better decisions about what goes in to DRAM and what goes in to persistent memory. What if you're willing to work a little harder than that? Then, oh, by the way, I put in the slides, I put an example of code. I forgot about that. This is what it looks like to use that library, libmemkind. Here I am calling memkind create pmem, which just creates the kind. And then, if you're a C programmer, you might be used to calling malloc and free for dynamic memory. But with memkind, it's called memkind malloc and memkind free. And it's really the same thing. Malloc and free, they take the same arguments as these do, except for these have an additional argument which says what kind of memory am I trying to allocate. Right, so it's like I say, it's terribly simple. If you're already a programmer who's familiar with the malloc interfaces. Okay. We have another volatile library. This is the newest addition to our PMDK. It's called libvmemcache. So this is for people who want to use volatile memory, and maybe you've even tried to use libmemkind, but you noticed over time you got memory fragmentation. You said, wait, I don't understand it. I should have a few gigabytes of memory free, but when I ask for this allocation of 500 megs, I'm told there's no more memory. Why is that? Well, usually that's some sort of fragmentation. You have all that free memory, but it's not contiguous. It's gotten fragmented over time. So to solve that problem, we built this thing that is an object cache that deals with the fragmentation for you. And we use this in our implementation of Spark. Right? It's a big data use case. So if you find that you're trying to use the volatile memory, but it's starting to get too fragmented for you, take a look at vmemcache. I did put in the slides a quick example of how to use it. It's a get-put kind of an interface. Here's a put, and here's a get. So it's like a key value store. And so you can take on your free time, you can look at this if you're interested. Of course, there's real man pages on the website. Okay, now let's talk about persistence. This is where it really gets interesting. So again, I wanted to make some of these APIs easier and easier to use. So we took all this other stuff that we've done and all these other libraries, and we made a nice high-level key value store. It's very easy to use, and it allows you to get quite a bit of value out of your persistent memory. It's called the PMDK, right there. There's a nice session on it coming up later today, which I recommend. And I show you a quick little example here. This is a C++ example where here I am putting a key and a value here, and here I am doing a get of the key to get a value. And I won't go into the details of the C++, but you know, there really aren't very many entry points here. There's like a get and a put, and there are a couple ways of iterating through all your values. So it's extremely easy to use. And not only is it extremely easy to use, it's actually quite performant, right? Inside, it has a pretty mature piece of software, a pretty complex engine in there that scales up really well in multi-thread programming. In fact, the guy who made it scale up pretty well is hiding back there. And do you have a talk in the summit?
Yeah, what about V2?
Oh, it's about V2?
Yeah.
Okay, well, anyway.
But I will show optimization for PMDK.
And he'll show you exactly, well, not exactly, but he'll show you some of the stuff that went on here. And so between Sergey, who's sitting right there, and Shimon, who's sitting right next to him, they're responsible for this very performant key value store. It's very easy to use. It's actually quite cool how it scales up. So you've got all the experts here. Corner them, make them tell you something. Okay, so what if that's not what you want? What if you don't want a key value store? You want something more powerful, more flexible. That's when you would go to libpmobj. This is our most flexible library. It allows you to do arbitrary transactions. It manages the allocation of the persistent memory. It has special primitives for doing persistent memory resident locking. It has primitives for doing some sort of reserves and publishes and lists. It has a lot of stuff in it. It's actually very featureful. Just to kind of give you an idea of what it looks like in C, here's a data structure that sits in persistent memory. And you can see here, I've got this little syntax here. So, you know, the C language, I didn't want to go modify the compilers, right? It takes forever to change a standard like the C language standard, right? And if I modify the compiler, then you'd all have to use my modified compiler, right? I wanted something that worked with all the common compilers out there. But C doesn't have a transaction syntax in it. So what did I do? Well, I went to this team in Poland, and we all worked together and came up with a great transaction syntax. It's about as good as you can get in C. It's done with a C preprocessor. So to start a transaction, you use this txBegin thing here. To commit a transaction, use txend. And so you can see it doesn't quite look like C anymore. It's got these macros in it. But it's not that hard to get used to once you try it. And so these are sort of arbitrarily complex transactions. You can do a begin transaction. You can change 25 megabytes of code, of data. And if your program crashes before you commit, that 25 megabytes of change is rolled back. That includes memory allocations and frees. We roll all that stuff back for you. So this is really good when you want to do your own, you know, like you want to create your own data structures, like your own hash table or your own tree or something like that. We give you the basics. This is what we used to create some of those higher level data structures. Finally, you know, you might say, this is really great, Andy, that's cool, but I want to do everything myself because I know a lot more about how I want my transactions to work. And I don't like what you've done. I just want to use the persistent memory. Can't I just use it, you know, completely raw and do everything myself? Of course you can. There's nothing that requires you to use PMDK. It's a convenience, it's not a requirement. But you probably want to use libpmem, no matter what. libpmem is this lowest level stuff, and it does those little flowcharts that I told you before, that these are the application responsibilities. libpmem handles that for you. So it's a small library, it's probably what you want. Just to give you kind of an example of the stuff that's in there, it has some convenience functions for calling mmap. It has functions that do things like copy memory and make it persistent afterwards. Right? It has things for flushing. So it's really just about copying and flushing. No transactions. Right? It's a very simple library, and it's what you want to use if you're really into building everything yourself. Okay, so that's kind of the summary of how you pick which library you want. I just wanted to make sure that I had a slide in here that showed you the kind of tools that are available to help you There are talks about a lot of these tools coming up later on in this summit. On the left-hand side, you see tools that are about provisioning and configuring the system to use persistent memory, right? On the right-hand side, you see the tools that are more about programming and working on your program. And probably my favorite tool, there are a lot of them, but my favorite tool is this, we have a Battleground Plugin. Battleground is a very popular Linux program that does things like help you find memory leaks. Our plugin helps you find errors that you've made in your persistent memory program. Okay? And we require Battleground to run on every example that we ever create that's in our repo. vTune has changes that have been made to it to understand persistent memory. And so if you want to understand those changes and see what vTune can do for you, go to the vTune session. And we also have this thing called Persistence Inspector that works on any binary. Doesn't require any instrumentation. And again, it tells you if you're breaking the rules. Like if you store something in persistent memory and then you make a change to it, but you forget to flush that change out, it'll give you a warning. So I've kind of tried to list the tools here. There's a lot on that slide. But like I say, we'll publish the slide so you can look at it. So what does it look like if I'm doing C programming? Like I told you, we used the C macro system to make transactions of syntax. There's a begin, there's an end, and then there are these optional sections. You can have code that only runs when you do a commit, only runs when you abort, or runs either way. And again, it's just because C didn't have a syntax for this. One of the kind of cool things about this macro, this begin macro, is it also offers to take locks for you. So this is a really important aspect of persistent memory programming. Even if you use our libraries or if you don't use our libraries, this one thing that we found out turns out to save us a lot of time. So if you want to hear this, it's that when you multi-thread a program, when you make a program multi-thread safe, usually that's done by adding locks, right? You add a locker in the critical section of code so that other threads don't see a half-done change. Well, it turns out that those critical sections of code are almost always the same places where you want to do a transaction for persistence. It's so common that we made this macro that both begins a transaction for your power fail atomicity, for persistence, and it grabs the locks you tell it to for your multi-thread atomicity. It does the whole thing in one atomic operation. Then you do your transaction, and when it commits, it automatically commits the transaction and drops the locks. These things match up so often that it actually made the code quite a bit simpler, and we were able to combine the multi-thread locking with the persistent transactions. Part of doing that was we made a special kind of a lock, a persistent memory lock. So if you have a data structure, let's just say you have a big data structure, like a big tree with millions of nodes, and you have a lot of threads operating on that tree, you might have, thousands of locks held at any given time. If that program crashes, or if that machine crashes, those locks are sitting in persistent memory. Some of those locks are in the held state, and some of them are in the unheld state. So how do you recover from that? Right? Reboot the machine, you bring it back up. All those locks are persistent, they haven't changed. Right? So we made a special kind of a lock, a persistent memory lock, that automatically is resetted when we roll all the in-flight transactions back. As we roll the in-flight transactions back, we change a generation number that automatically resets all the locks. It's just one store. And it gets millions of locks in one store. So it's actually pretty cool. And it's a nice feature of our library. Okay, I want to give you a taste of the C++ programming, but there's a longer session tomorrow on C++ programming that I recommend that Shimant's going to teach. And so basically what it looks like, it's quite a bit different from C because we could use the type system in C++. So C++ has this type system that has these things, these little templates that you see with the angle brackets here, right? So this is not, we didn't change the syntax in C++. Everything I'm showing you is C++ correct syntax today. And what you do is if you have a data structure that you want to live in persistent memory, you indicate it with this little P template here. See that little P? That says that value is a persistent memory resident uint64t. And this little persistent pointer template here says that next is a pointer to a PMEM entry. Okay, and it is a persistent memory. Now that we have those templates in place, the type system can automatically record all the changes to those things over time and make sure that they're persistent in the correct order. So it gets rid of a lot of the macros that we had in the C version. Actually makes the programming pretty clean. Let me show you an example. Here's a push operation on a queue, and you can see I've highlighted with the gray area here what's transactional. Everything between these little curly braces, the open red curly and the closed red curly. And the stuff in the middle looks just like what you normally write. You're just allocating a node and you're linking it in. It's just, in fact, it's almost identical, except for instead of calling new, you call make persistent. But other than that, it's pretty much identical, the code. But everything here is transactional. It either happens completely or not at all in the face of failure. So it's just, this is just normal C++ syntax with us using the type system. Okay, so this is a talk that was on the essentials of PMDK, right? So I kind of whizzed right through it. I showed you all these libraries, how you choose which library to use. I showed you some C examples. I showed you some C++ examples. I do have, according to my watch, I have like 2 minutes left. So I can stop and take any questions, and then we'll go on. So anybody have any questions about PMDK or anything I talked about? It's all so clear, right? Yeah. So transactions are mostly done with an undo log. So mostly when you make changes, we write the old value to the undo log. And then when the transaction is committed, we just throw away the log. I say mostly because some things turn out to be faster internally with a redo log. So we also have these little tiny redo logs that are used inside the library. But for all user data, it's all undo logs. And so it does require copy every time you change something for the first time in a transaction. We have to copy the original name.
That means it need to reserve some special space for it.
Yeah, the library does that in the file itself. So you tell the library where the file is that you want to store your data structures, and it puts a header at the beginning, and it manages the allocation of space, and that includes the allocation of the undo logs. Exactly right. There's one back.
And the other side. So yeah, I noticed that you add new micro keys begin and the parameters which can have lock, right?
Right.
So for the lock, it's a DRAM lock, or it's a persistent memory lock.
It is a persistent memory lock. It's one of our, we call them PMEM mutex Ts.
Okay.
And so we have them for all the different POSIX styles of locks. We have all the, there's read-write locks and mutexes and condition variables. We support all those. Most people just use mutexes. But they're these special kind of locks that automatically get reverted.
Mm-hmm.
And that way, when you roll back the transaction, the locks don't end up in a bad state. And you're free to use your own locks. This is just for convenience.
Yeah, so you mean that we can use volatile memory?
Absolutely. In fact, our locks do use volatile memory. When I said they're persistent memory, they look like they're resident in persistent memory, but at runtime they actually get allocated to volatile memory, probably for the same reason that you want to use volatile memory for performance. Yeah.
Okay, the second question is about if I allocate something to the JLog and a PMDK library, and then I try to use PMDK to do the persistent memory copy or whatever.
Yeah.
Like doing is okay, right? I guess.
Yeah. Yeah, you're perfectly welcome to mix these things. It's just, you want to make sure that if you're using the PMM ops for a transaction, that it knows that you changed something. So if you want to change it in a way that's not obvious to the library, you have to call a little API to tell us you changed it.
Yeah, because we want to skip the overlap transaction in some case. We don't really want to go back.
Absolutely, and there's nothing wrong with that. You're absolutely allowed to do that.
Okay, thanks.
Yeah, you bet. Okay, I think our time expired. Thank you very much. Oh, you got something out of the top.